Okay, good morning, everyone. Today's distinguished webinar series featuring Dr. Morteza Hashemi. And Dr. Morteza is an assistant professor with the Department of Electrical Engineering and Computer Science at the University of Kansas, Lawrence, Kansas. He received his master's and PhD degrees in electrical engineering from Boston University in 2013 and 2015, respectively, and his BS degree from Sharif University of Technology in 2011. Before joining KU in 2019, he was a postdoctoral researcher at The Ohio State University. His research interests span the areas of network cyberphysical systems, wireless communications, and information systems. In 2021 and 2022, he was a recipient of Bellows Scholar Award from the University of Kansas. Dr. Morteza, it is an extreme honor to have you as part of the webinar series at the University of North Dakota. I'm so grateful that you accepted our invite and appreciate your time today, and we're eager to see your presentation. The floor is yours.
Wonderful. Thank you so much for your kind invitation and also the introduction. It's my honor to be here. And yeah, very glad to be joining this webinar, which sounds very amazing, very organized webinar. So looking forward to see future webinars as well. So let me start sharing my screen.
Great, we can see you. Yeah.
All right, wonderful. Hello everyone, and thanks for joining this webinar. So today we are going to present some of our recent results about using multi-agent reinforcement learning control for cyber-physical systems. However, specifically, I'm going to focus on smart grid systems as one example of cyber-physical systems. So this is the agenda of the talk. So at the beginning, I will just start with overviewing of cyber-physical systems, and then I will go through two specific scenarios that we will see that what are the challenges with the current and the future smart grid system, and then I will conclude the talk. So starting with the introduction and a motivation, this is a very high-level overview of a cyber-physical system. So what they are actually integration of some physical components plus some virtual, some cyber components. So, and we have seen and we are working with them on a daily basis from a smart grid system, cellular systems, Wi-Fi, UAVs, electric vehicles, some kind of a storage or a cloud computing, and even a robotics. So there are, these are just some examples of a cyber physical systems that we are dealing on a daily basis. So here, I'm kind of capturing and summarizing that what are the main building blocks of the cyber physical systems. So I have called basically this kind of this paradigm as a connected intelligence. So what do we mean by that? Meaning that almost any of the kind of the cyber physical systems that we consider, they have some key components. They have some sensors. They are connected to the storage and a cloud. They are using some sort of a communication networks, different technology, and definitely using or expecting to use some sort of machine learning and AI solutions. So how all of these kind of, they are both creating opportunities and at the same time challenges. So when we are talking about the networking and the communication technology, that means that now we are not just dealing with a one agent. So basically there could be a distributed agents and distributed parts or the different parts of the cyber physical system that they can communicate with each other. So one key component then is that we are dealing with the distributed systems. What's the next basically component is that this machine learning and AI coupled with the sensors, basically it kind of enable us to develop some data-driven decision-making solutions. Why? Because all of these sensors, so there would be so much of a data that these cyber physical systems, they are generating. And machine learning and AI, we can use them to kind of come up with sequential, for example, decision-making solutions and frameworks. So the focus of my presentation today is around these two topics and these two concepts, distributed systems and also data-driven decision-making frameworks. However, in this talk, we are just going to focus on smart grid systems as an example of a CPS, just to make our discussion a little bit more concrete. That's the reason that we focus on smart grid systems. And we are interested in developing data-driven decision-making solutions. And as I mentioned, we are focusing on two specific challenges and at the same time opportunities. So I will discuss that there are both good news and bad news for each of these two scenarios. So the first scenario is that we are considering a large scale integration of a distributed energy resources, or DER. Another scenario is that there is actually exponential growth in a number of electric vehicles that they are being integrated into a smart grid. So on one hand, it's very good news for the environment and other factors. On the other hand, the smart grid system is not designed to support these many EVs. And we will see what would be the challenges with this increasing number of EVs. So each of these scenarios now, in order to make the challenges a little bit more concrete, we focus on uncertainty. So what does that mean? It means that there are some components that we cannot estimate, or we don't have a good model in order to basically come up with the realistic system model and use maybe some traditional optimization problems. So that's a reason that basically to deal with the uncertainty in any of these two scenarios, and we are proposing multi-agent reinforcement learning solutions. And why multi-agent? Because as I mentioned, we are dealing with a distributed systems. It's not a one centralized component. So if we consider a smart grid systems, there are just so many different pieces and components that they are distributed. They are not in a one place that we can just train a one single agent reinforcement learning agent to make the decision making. So with that, basically, this is our goal. So we want to leverage multi-agent reinforcement learning frameworks for each of these two scenarios with the understanding that there are uncertainty that we need to deal with. So with that, let's dive a bit deeper into the first scenario, which is a large-scale integration of distributed energy resources. So these two plots, it shows the changing trend of basically energy generation by different sectors. So this is from 2010 up to predicted into 2050. And this one, it's basically from 2022. So after that is basically forecasted values. However, we see that the good news is that the renewable energy, they are such as a wind and a solar power, they are actually being integrated into a smart grid, and their portion keeps increasing. So we see that here, for example, it's expected to be more than 40% as a renewable resources. However, on the right side, what are the different portions? What are the different basically renewable resources? For example, the solar and also the wind. So these are the two biggest players that they are contributing to the renewable resources. So far, this is good. However, the bad news is that when we compare with the traditional energy resources, these renewable resources, they are unpredictable, depending on a different environmental factors. For example, depending on the weather, depending on the wind speed, and all other different things. So there is uncertainty associated with these resources. Let's look at from another perspective. Okay, from the cost. So this one, it shows the cost per megawatt hour. So how much does it cost to use any of these type of generation methods to generate 1 megawatt hour? So we see that over a time, the cost, for example, for a solar panel and a wind, it keeps increasing, and especially for a solar panel. So that's a good news, that basically the main problem with the renewable resources or renewable generation, it's kind of going away. However, the bad news is that now the lower cost, I mean, having a lower cost is a good news in general. However, when we have a lower cost, then there is a large-scale integrations of these distributed energy resources. There are more and more houses that they are installing the PV panels. So now we have so many of these PV panels, they are distributed across networks, and each of them, they are generating some amount of energy, and they are injecting to the system. So then the question is that how can we handle such a large scale scenarios? So in order to address that one, so we aim to develop this distributed decision-making frameworks with 3 key goals. The first one, it's all about the economics, meaning that we aim to provide economic benefits for both electricity providers as well as the end user. So end user here is, for example, the households that they are installing the PV panels. The second goal and the third goal is to how can we achieve this one using some dynamic decision-making frameworks. And as I mentioned, we would like to achieve these 2 goals with the understanding that there are an inherent uncertainty and an imperfect state information that is part of the system. We cannot estimate basically the state of systems and input those with to the reinforcement learning algorithms. So these are the 3 goals that basically we would like to achieve. So let's dive a bit deeper into the system model. So this is a current system model. So some jargons here. So we call presumers. What are the presumers? These are the households. So the presumer is the households with the PV panel. So they are producing energy and also consuming. And of course, we have a traditional consumer as well. There's an ISO, independent system operator. It's not a focus of our talk. So, but it's some independent organizations that they are kind of responsible for regulating the electricity market. Then we have a LSC, which is a load serving entity. So this is an entity that we are basically on a monthly basis, we are receiving electricity bill from these companies. So then the LSC, so let's walk through each of these ones. So presumers produce energy to meet their demand. They can charge their battery. So we assume that there's a battery associated with each of these presumers. And during a peak times, for example, when the price is high, they can also sell the electricity back to the grid. So we assume that there is this bi-directional exchange that could happen. However, for a consumer, it's just a one-directional. Basically, they are just purchasing electricity from LSC. So these presumers now, they are distributed across the network. So basically, they are a distributed market players. On the other hand, we have the LSC, which is the load serving entity that is a distribution utility company and is responsible for aggregating the load from all of the end users and the residential users. And it's going to be responsible and is committed to provide those electricity to those end users. So therefore, LSC is going to purchase electricity from the wholesale market and then resell it in the retail market. So there are 2 types of a market here, the wholesale market and a retail market. So, and then if we consider from a wholesale market perspective, there is also a wind power plant and conventional power plant. So the conventional power plants, they are more stable. There are not much changes in terms of their generation level. However, the wind power plant, as I mentioned, they are not predictable. Up to some extent, we can predict the wind generation. However, there are some uncertainty associated with the wind power plant as well. So now let's dive a little bit deeper into the mathematical modeling of a presumer optimization. So this equation, and I wouldn't go through too much details here, just at the high level. So here, each presumer, the amount of energy demand that they have is basically the amount of a consumption minus the amount that is being generated by their PV minus the amount of basically energy charge or discharge from a battery. So this E could be plus or minus depending if we are charging or discharging. And then, as we said, our goal, the first goal, is about providing economic benefits, meaning that each presumer, they are basically interested to maximize their revenue, or conversely, they want to minimize their total electricity bill. So how this electricity bill is calculated? So there are two key components here. One of them is this C cell. This is basically the selling price, and this one is a buying price, meaning that and this lambda tilde I is basically a binary variable. It could be either 0 or 1, depending if we are selling to the grid or buying from a grid. This would be basically our revenue. So now, what's the decision variable of this presumer? So basically, they want to decide if they need to charge or discharge from the battery, given of the observation that they have from a sell price and a buy price. So on the other hand, from an LSC perspective, LSC is also tries to maximize its total profit, because this is, again, our first goal for each of a market player. However, the LSC needs to incorporate different uncertainty components and sources. For example, from a wind power generation, because remember that the LSC on a one side is basically interacting with the wholesale market. So is buying the electricity from some of these wind power generations, right? But on the other hand, there are some PV rooftop panels as well, the distributed market players, and they are also selling to the grid from a retail market perspective. So here is the total cost of a LSC. So again, I wouldn't go through the details, but now one thing that we need to also consider is that LSC that works from both the wholesale market and a retail market. In a wholesale market, they have this market that is called day ahead, meaning that 24 hours before, so every time basically they purchase electricity and commit to purchase some amount of electricity, basically 24 hours before. So that one is called day ahead. And then there's another market, is a real-time market, meaning that on exact time right now, what is the total demand and what's the price of electricity. So here we see that there are three main components. One of them is the amount of basically cost that the LSC pays for a day ahead market. And then there are some amount of electricity that buys from the PV, basically from presumers based on this buy price. And also there is some mismatch that if basically the amount of the real-time demand and a day-ahead demand, they don't mismatch, and basically they don't match, then we have this basically load uncertainty or a load mismatch. So then the LSC is going to also purchase that amount of electricity with the real-time price. So overall, then the LSC net profit would be, the LSC is now selling the electricity in a retail market. So this is the amount of money that the LSC is collecting from a residential user. So this is the summation across the traditional consumers, and this is across the presumers, minus the total cost that the LSC has spent in order to procure that amount of electricity. So now what are the decision variables that the LSC can actually play with and can set is the electricity buy and a sell price. So this CS and a C buy here. So to solve this one, we developed this multi-agent deep deterministic policy gradient, or a DDPG algorithm, that is integrated with a long short-term memory, or a LSTM forecasting. So we will see that why we need this forecasting as well. So at the load serving entity, or the LSC, we have this agent, we call it LSA. And then at the presumer, also each of the presumer, they have their own agent, we call it PA. And then we use a LSTM, because remember, there is one wind power plant at the wholesale market that is also generating electricity. However, the LSC needs to commit in a day-ahead market. So LSC needs to have some estimate that within the next 24 hours, what's the amount of a wind generation. So then we use this LSTM in order to forecast what would be the wind generation over the next 24 hours. So here just one kind of very general kind of demonstration of reinforcement learning and a DDPG. So we have an environment, there's a state, reward, and action. So DDPG, it has one kind of a unique structure that it has an actor-critic kind of a structure that the critic is basically based on the Q values, and then the actor, it would kind of make the action. And then, of course, they are dealing with the replay buffer and applying the action to the environment. So this is just a very generic DDPG architecture. So therefore, now if we kind of split our electricity market, then we have two agents. One of them is a LSC agent, that the goal is to maximize the profit, and also the presumer agent, that the goal is also for the presumer is to maximize their profit. Of course, there are different constraints for each of them that I wouldn't go through this, but as you know that I'm in the power system, it's, I mean, there's so many physical constraints as well as regulatory constraints. So basically these agents, they need to follow all of these constraints, but at the same time to maximize their profit. So here is a little bit more detailed kind of a view of what we have basically implemented and achieved. So we have here, basically the microgrid is our environment. So basically we implement this microgrid model here as an environment. Then we have the LSA or the LSE agent, the load serving entity agent that is dealing with the environment. And then on the other side, the presumer agent is also interacting with the environment. However, there is this LSTM network as well, that it takes the input from all of the wind power, all of the informations that are basically from a wind power plant in order to predict what would be the wind generation over the next 24 hours. So we use this time series forecasting to capture the wind uncertainty, and then we have this multi-agent RL algorithm to capture the dynamics in a retail market. So here are some simulation results so this plot, it shows a demand efficiency power, meaning that how much mismatch we have between a day ahead and a real-time demand. Meaning that, okay, we have estimated that in the next 24 hours, what would be the demand, but in a real-time market, the demand could be more or less than that. Okay? And then we will see that basically the positive or a negative value, that it shows that there's a higher or a lower real-time demand. So whenever we see that basically the demand efficiency increases, meaning that at the real time, so basically when we have a positive demand efficiency, it means that there is a higher real-time demand. So in this case, now our DDPG algorithm or a DDPG agent is able to learn what should be the price. Because remember that for a LSC, the action or the decision variable is electricity price. So whenever the demand efficiency increases or becomes positive, then LSA increases the price as well, so that it has two impacts on the presumers. One of them is that they are encouraged to reduce their consumption. On the other hand, whoever has basically additional or excessive power in a battery, now they are encouraged, incentivized to sell back to the grid, because the buy price and the sell price, we keep it the same. So therefore, by increasing the price, we can basically manage the presumers and the consumers in two ways. One of them is that to reduce their demand, and another one is to incentivize them to help the grid and basically sell back to the grid because the price is just high. So, and we have compared actually this. So this, the blue plot is our the RL algorithms, the price, the dynamic pricing that the RL has come up with. And the other ones, these are some, for example, fixed price baseline. Another one is a time of use that Evergy is, for example, is a one LSC that is active in Kansas and Missouri, or Edison. It's another utility company that they are using this waveform. So as you can see, these are a predetermined waveform. So these companies, they are not using AI or the ML to come up with the dynamic pricing. So we will see that in terms of a comparison, in terms of a performance metric, that this fixed price or a time of use, compared with our algorithm, basically they achieve a smaller profit for this utility company. So here I haven't included the results from a presumers, but from a presumer side, we can also see that basically this method is in benefit for them as well. Here's another parameter, peak to average ratio. So it's a little bit more power related kind of a metric. And we want to decrease the peak to average ratio, meaning that we don't want to have a very high peak value of a demand and then the average to be very small. So a smaller peak to average ratio is better. So basically, we will see that basically our method with this dynamic pricing, it actually achieves a smaller peak to average ratio. So this was about the first scenario that we were mostly concerned about the integration of a distributed energy resources. So a couple of the key features was about these distributed PV panels that they are able to sell back to the grid. Then the question was that, okay, how much they need to sell, and from an LSC perspective, what's the right price to set in order to incentivize them. So now in a second scenario, we are looking at some other basically new kind of players that they are becoming more important for a smart grids, and those are electric vehicles. Electric vehicles, so again, the good news is that basically we are experiencing a growth in the number of electric vehicles, which is good for the environment and all other factors. However, the bad news is that now we have this some new sources of uncertainty and a demand. And we saw in a previous section that with this dynamic pricing, now we need to see that, okay, how would this EV charging control would behave and react to dynamic pricing. So in a second, basically in this section, our focus and our assumption is that the dynamic pricing is going to be implemented with the LSC. Now the question is that how can we design distributed EV charging control algorithms in order to be sensitive and responsive to the dynamic pricing. So this is a system model. Consider a residential area, for example. There are a bunch of networks, and each of them directly connected to the first level distributor, for example, transformer. So we focus only basically at this level. We are not going to discuss about the wholesale market. It's just at the lowest level, the interaction between the residential users and the distributor, the first level transformer. So what is happening is that now assume that each of these residential or each of these users, they have a one EV, and they are basically equipped with the EV charging controller. So the current EV charging controller, for example, from Tesla, they are operating according to a predefined pricing structure, meaning that they assume that, for example, Edison, which is the utility company we saw, that they have this predefined pricing structure, and then this smart EV charging controller, they decide how much they charge the EV and at what time they charge the EV. However, when we basically implement this dynamic pricing, then this EV charging controller, they cannot they cannot respond or be responsive to a dynamic pricing. So what is one feature of a dynamic pricing that we need to capture in this section is that the distributor set the electricity price, as we saw in a previous section, and the EV networks basically, we have some total network consumption that the distributor is able to observe. So basically, this is one kind of a policy or a rule. So the distributor would set the price. If the total network consumption increases, then the electricity price will increase as well. And as we saw in basically the LSC dynamic pricing scheme, we saw that if a demand efficiency increases, then the price increases to incentivize the user to bring down their consumption. So this is the only kind of a policy or a rule that we are going to assume in this section. So now we have this basically uncertainty from a price perspective, that from end users, they don't know what the price is going to be, right, in the next 15, 20 minutes or in the next 1 or 2 hours. So our goal here is to design the optimal charging controller for this EV network. So given of this dynamic pricing, and also there are some quality of experience requirements. For example, as an EV owner, for example, when we arrive, we are expecting that within 2 hours, our car to be fully charged, right? So there are some requirements in terms of arrival time and departure time. We don't have like 24 hours waiting for the EV to be charged, right? So there are some requirements in terms of the quality of experience as well. So now, what is our proposed solution is that we are saying that each of these households, they can have this AI or ML algorithms, and this AI or ML that is going to be implemented using reinforcement learning again is going to manage and basically specify the optimal rate of the charging, given of all of the constraints, given of the quality of experience constraints and other physical constraints of the network. So how we can achieve this one? So let's dive a bit deeper into the mathematical modeling. So we consider a distribution networks, basically as a graph. So the number of end user is capital N. So the goal is basically LIH is the total consumption of node I, or basically the household I at time H. So this is a summation across all of the appliances within that household, for example, right? So this XI is all the set of all the appliances, and then so we sum it up across all of those components. So we can consider that, okay, there are some kind of a non-EV component and there is a one EV component. So because our goal here is to design the EV controller algorithm, so without lack of a generality, we assume that the other appliances, they just added some baseline addition. So our main focus is to come up with basically the right schedule for this XI EV for a time of H. So again, our goal is to minimize the total cost that the EV owner is going to pay, right? So across capital H hours, so this would be the total cost that we are paying. But what we are saying here is that this CH is a cost function, is a price that we don't know what the LSC is going to set the price at, but we know that is a summation, it's a function of a total load of a network, meaning that if the load increases, then this C of H would have a higher value. So this is the only knowledge that we have. So basically this C of H denotes the cost function at time step of H and is a function of a total load within the network. So obviously we can solve this one in a centralized fashion. However, we need the information from all of the end users. Okay, we need to know exactly at any given time what's the total consumption of any of the users. Then, with some maybe estimation, we can come up with the estimate of the cost and then minimize this function. However, that obviously is not feasible to come up with the centralized solution. So now the goal is to find a distributed solution. So in this case, we define BIH as a kind of the amount of a billing or the amount of basically the electricity bill that is going to be charged to the user I by the LSC at time slot H. So we assume that this is proportional to the usage, right? So for two different users at the same time, so again, this is dependent on a time H because we have this dynamic pricing. So it would be proportional to the amount of their use. So if we use this kind of a logic, then if we go through some machinery that I wouldn't go through the details, then the total cost of one specific user, the amount of basically the electricity bill for that one for that specific edge, it would come up with this function. So let's kind of see what does this function look like. So now we want to minimize this function. So C of H, it was a cost function. So now the C of H is a function of the that specific user plus the consumption of other users. So basically, times some constant value where we are not concerned about these coefficients. So this basically optimization, now we see that it's a function of a local consumption plus the other users' total consumption. So again, if we know the total consumption of other users, definitely we can solve this problem and we can minimize this one. However, this is a big assumption and it's not feasible in reality that we know that, okay, our neighbors, how much they consume in total. So the goal here is that each of these nodes or the agents in a network, they can somehow adjust their consumption so that collectively they can bring the cost down. So if you consider it's like a game that if each of them being selfish and then they charge at a very high rate, then the cost would, basically the total consumption would increase. And then we know that the cost would also increase with the total consumption. So somehow they need to learn to cooperate with each other without exchanging information between each other. So it's kind of a distributed control without observing the information of everybody else. So again, we are using a DDPG to kind of solve this problem. And each of the EV owner or each of the households, they are equipped with a one DDPG agent. So some machine learning kind of a context here. So we assume that there is this N agents. So there are some policy parameter, for example, theta 1 up to theta n. And the policy for each of the agent is denoted with pi 1 up to pi of n. So we implement two variations of this multi-agent reinforcement learning. One of them is called independent DDPG. So in an independent DDPG, so this is basically the overall, so DDPG is a policy gradient, as you are aware. So in a policy gradient, basically we have this equation. So there are two basically components here. There's a Q function and there is a policy pi itself. So what does this independent DDPG mean? It means that each of the agent I, so I here is the index of the agent, each of the agent I, they only have access to their own observation and their own action. And of course, it's parameterized by the value of a theta. And then A of I, which is the action of the agent I, is a function of its own observation. So we have an independent actor and an independent critic. So if you remember, DDPG is based on an actor-critic structure. So here, we see that basically the critic is related to the Q function. We see that the Q function, the input to the ith agent, Q function is only the observation of its own. So it doesn't collect any information from other agents. There's another concept, it's called centralized training and a decentralized execution. So this one, it says that at the time of a training, we let the agents, they talk to each other. They share their information. For example, here for the agent of I, it has an input from an observation of all the other agents as well. So observation of 1, action of 1, up to observation of n, action of n. However, at the time of execution, which is a policy, it only observes its own observation. So it doesn't have access to all the observation of other agents. So this is a kind of we call it independent actor and a joint critic. So there is a single critic here that it basically has access to the observation of everybody. But at the time of execution, we disconnect the critic network and just use the actor network. So here is a kind of a little bit more details at how CTDE works in practice. There's a training portion that all of basically the Q functions, they have access to the observation and action of all of agents. But once it's being trained at the time of execution, it's only the actor networks that it would be operating for each of the agents. So here is a little bit more details that I guess for the sake of time, I wouldn't go through the details. What are the action set and observation set for each of the agents? Just a one note that the action set or the action of each of the agent is the power rate that we charge the EV. So here A of I is the rate at which the ith household is charging its own EV. So this is basically the optimal action that we want to get. Of course, there are some constraints, some observation, meaning like at the battery level, what's the arrival time, what's the departure time. So at the time of a departure, we want the battery to get to the expected level of the charging. So if you remember, we were discussing about the quality of experience that at the time of a departure, we would like to have the battery to be fully charged or at the level that the EV owner is basically specifying. So these are all of the observations that this multi-agent RL, they are basically observing and then determining what's the charging rate that the EV should be charged at that rate. So in terms of a reward, we have defined this one. So basically it's kind of, we want to basically have the cost and also the quality of experience, meaning that we want to get to the level of expected battery level at the time of a departure. So some simulation kind of details that are here. We use some random kind of distributions about the arrival and a departure time. So here are the comparisons. So what we are interested to compare is to compare the CTDE, DDPG, and also independent DDPG. So we see that both of the algorithms, basically they can get to the charging level of the battery. So in both of a scenario, basically the charging control mechanism effectively charge the electricity vehicle. So this is good. However, if we kind of dive deeper into the action of each of the agents, so here we see that the independent agents that they have an independent critic, so they have a lot of fluctuations in the basically charging of a battery. This is not good in terms of a physical or the health of a battery as well. However, the other one, the CTDE, it has a much smoother charging or the change between different actions. Another kind of a set of a result is the average return for, so here we have for the 3 and 5 agents. So average return, we see that both of these two algorithms, they achieve almost the same level of a return and also the amount of a variance. So there has been a lot of very recent discussion that does decentralized training and a decentralized execution, is it helpful or not? And here, I mean, we are kind of investigating that in terms of empirical evaluation, if they are kind of helpful or not. But our initial results, it's kind of shows that it seems that both of them, they achieve the same level of average return. However, one important point is that in the independent DDPG, some of the agents, they are not able to converge, meaning that we have some agents that they are just not converging, and some other agents, they can converge. However, in a CTDE, we are basically reducing the variability across different agents. So everybody, they are trying to converge together. So here in this plot, we are plotting the learning stability. So what does that mean? It's the ratio between a best performing agent, I mean, the ratio between a worst performing agent divided by the best performing agent. So here is between less than 1. So we see that when we have a 3 agent, it's okay, still they are similar, but when the number of agents goes to 5, the independent DDPG, basically the ratio between a worst case and a best case keeps kind of decreasing. However, the CTDE, basically it's more fair across all of the agents. So this one, we call it learning stability, is more stable across different agents. So let me conclude this presentation. So in this research, we have focused on a distributed control algorithms for smart research systems. With the main focus on uncertainty, we discussed about this large-scale integration of distributed energy resources, as well as large-scale integration of EV into the smart grid. So we have developed this multi-agent DDPG solution for each of these scenarios. And specifically in the last part, we have been contrasting the decentralized basically execution and a CTDE versus independent DDPG. With that, I will stop here. Thank you so much for listening to this presentation, and I will take any questions.
Thank you, Dr. Morteza. First of all, thank you. And it's a very interesting presentation. I think you have nailed it, the way you presented your work in a very easy to understand manner, and at the same time, a lot of important problems that you actually talked about, in the modeling, for using multi-agents. So we'll leave questions now, so folks can able to put their questions. I think we have some questions here. Let's see. Thank you for the wonderful presentation. My question is, from which scenario do you think will be more efficient while evaluating the cost function and energy saving concepts? EV fleet contributing to demand response, or EV fleets participating in vehicle-to-grid operations?
Yes, this is actually a wonderful question. Thank you so much. I guess, here we haven't really considered the V2, basically the vehicle to be basically helping the grid. Of course, in the first part of my presentation, we had the presumers that they can inject back to the grid as well. But in the second part, we are just considering that basically vehicles, they are as a consumers, and basically how much we want to control the rate of charging at any given time. In terms of, I guess, energy saving concepts and a cost function, to be honest, we haven't considered this scenario yet, but definitely this is a very interesting scenario to kind of consider that how much the vehicles they can kind of contribute to the grid.
You're right. I think your talk is primarily on modeling of this so-called looking at the uncertainties of this explosions of DE,
right.
And I think I really enjoyed that two scenarios that you talk about, this independent actor and joint critique, and independent actor and independent critique. In your simulation results, you talked about this average return did not converge for one scenario versus the other, but you have very limited number of agents that you use. How do we justify this, smaller number of agents, even though it's great to do the modeling and simulation aspect? How do you foresee in terms of, from a computational point of view, when we see growing number of DERs that actually, are growing, even though it's a good news from the emission point of view, like you said, but, when I talk to a lot of people, they say, the number of DERs also talk a lot of nuisance to the grid, because we don't have those interoperable. There's a lot of power quality issue, interoperability issues, and our grid needs more, modernization in that aspect. So, I know that this is a very, open-ended questions, but I think I'm just curious to see, how do you plan to extend this particular work, what you have done? There are a lot of merit in this. I think there are a lot of things that you can able to, as you go on, but I'm just wanting to listen from your perspectives as you want to take on the project. Could you please shed some light on that?
Sure. Yeah, definitely. As you mentioned, here definitely, the number of agents that we have simulated is very limited. We have literally right now, for a 10 and 20 agent is running. So my student, I'm waiting for his response. But from our initial investigation, it seems that, yeah, I mean, in terms of average return, that they are similar. However, we have seen very recent, like a few months ago, some theoretical developments and a proof that actually in practice and then in a mathematical proof that they can show that the average return is similar. And even in terms of a variance, that how they are actually being compared with each other. But yeah, definitely. I mean, this is a kind of, I believe, open-ended question about the multi-agent, right? So if we use this MDP or a decentralized MDP kind of a context. So right now we are working on that one, and we have started some collaboration with some like a mathematical department as well, because I mean, under the hood, there is a lot of kind of a statistical modeling that we need to incorporate into basically these two framework as well.
Good.
But yeah.
I think the following up our questions while we wait to other questions too. In terms of this DDPG algorithm, yes, people are already exploring. There are so many papers on there on reinforcement learning, and there are different ways to model this. And one of the things that I'm always puzzled about this, I just came from this NAPS conference last week, and we had a vice president of Duke Energy giving a talk on how climate change is affecting, our grid, and they continue to experience outages. There's so much of, so much of this. Texas outage, for example, a couple of years, the lack of winterization has cost completely, a different ballgame of how to prepare for it. And the prices were so high in some work hour periods. You talk about, increasing the price, but how do we accommodate fairness into the model? And because, and there are some consumers who have seen an exorbitant amount of price in certain peak hours, which is not morally, acceptable to the society. When we model these things, and yes, you may want to increase the price if there is no participation, but as a simulation experts or modeling experts in terms of this thing, I think, when the net consumptions increase, yes, we need to increase the price, but is there a way that we can able to figure out a way to say some optimal way to do that? And you mentioned about two companies, Edison and I can't remember the other one, but time of use. But how do we engage with electric utilities to convince an argument, make an argument to make us say that, hey, you need a different way to handle these different shapes of curves that actually need to be fair in some sense to, I don't know. I just wanted to see what you think about that.
Yeah, definitely. I mean, yeah, this is an excellent point. I mean, in our simulation and in our modeling, we have let the minimum and a maximum of a price such that the average would remain the same. So we have we don't kind of increase the price to some like crazy values. And I remember it was a few years ago, maybe in Texas, that there were kind of some outages and the price hiked a lot. And then some people, they saw a very large increase in their electricity bill. I mean, here in our modeling, we try to keep it as fair as possible with the other. For example, I know that from a regulatory perspective, there are some kind of a policy that they need to keep the average, or maybe there are some constraints that they cannot just keep increasing. And of course, I mean, about the open market, I mean, maybe in some areas there's a monopoly, so the people, they don't have an option. However, on the other hand, I guess, I mean, it's more about, I guess, a market design perspective, that how much you can increase before you lose your customer, and then they switch to some other companies. But from a pure RL perspective, I mean, we have set the maximum to be such that, I mean, across some Monte Carlo simulations, basically the average of the actions that we take through the RL would be the same as the other pricing schemes.
When you mention average return, what does it mean, in terms of your simulation? How do I read that?
Oh, this one. So basically, this one is the average. So at every episode, so for each agent, we have basically reset the seed. Basically, the randomness is changing, so that basically we regenerate the observations and all of the randomness in the system. So we change that one and run it for 10 times, I believe, these simulations, and then average across all of the agents. So it's a kind of a statistical average across different runs, and then different across the agent as well.
So what does it mean for that agent? When you have more returns per agent I versus agent J, what does it mean? How do we read that?
So, I mean, first, it was kind of a minimizing the total cost of that EV, right? So basically, it shows that, okay, that agent is finding a better solution, right, in terms of the charging control, that how much it should charge, so that the total cost and also those quality of experience, meaning that we are closer to the expectation of the EV owner when, for example, the departure time arrives, that basically wants to leave. So basically, I mean, it's just a combination of that, right?
Okay, we have another question. From a prosumer perspective, battery degradation, data security, privacy are major concerns to this transition. How do you think it can be regulated and engage participation in this kind of framework? In your optimization model, have you taken into account on battery efficiency and capacity to evaluate your output?
Yeah, I guess so. Let me start from the last one. Yes, so we have incorporated the battery capacity, state of the charge, and all of those details, but we haven't considered the battery efficiency or the degradation in a battery. So we don't have very, I would say, exact modeling of a physical layer of a battery, but at the very high level, we know the limit, we know basically the charging rate and what should be the nominal rate that we cannot charge more than that. What's the state of the charge? So we have those constraints. I kind of didn't include those here just for the sake of
We have some great students asking nice questions. And in another one, as you pointed out, scalability is concerned with the model. So have you considered integrating graph neural networks to improve generalization and transferability of RL policies?
Yeah, this is an excellent point. I mean, we haven't considered the GNN for this work, but definitely, I mean, I have seen some research works that they are using a GNN to kind of capture the underlying, basically the structures of a GNNs, because I mean, there are some features that are hidden inside of this network as well, that the GNN potentially can capture and explore those. But we haven't considered it, but yeah, it's an excellent point.
Thanks for this presentation. Is it possible to share the presentation file? Do you think we'll have access to the slides? We can able to make it available on our website? Is it doable?
Yeah, I believe so. I mean, yeah, I mean, most of it. So I will just include the references to our paper so that we know. I mean, if somebody wants them to see more details, I will just include it. But yeah, definitely I can follow up and send you the slides.
Super. And again, thank you so much for your time today. I know you're in the conference, so I think we'll wrap the session right now. And for the time and contribution, you will receive a plaque from UND and signed by or a letter from a dean as well. So could you please share your mailing address via email? We'll figure out a way to send that plaque to you. Thank you, Dr. Morteza, for your time. And I look forward to collaborate with you as we learn more about each other's work, and appreciate your time today, and have a safe travel back to your Kansas.
Yeah, thank you so much. Yeah, thank you so much for the invitation. It was my honor and pleasure to present today. And yeah, looking forward to continuing our discussion and extending the collaboration.
Thank you.
Sure. Thank you so much. Have a good day, everyone.
You too. Bye.